Good morning. I think it's still morning. Yeah, good afternoon. Good afternoon, everyone. We are going to get started. What I've decided to do is change things. Hopefully they won't change much more in the future, but this first week's been weird. So the things that I've changed is I've moved the homework for week 1 into week 2, and week 2's homework as well. So for those who need it, I've given you some more time, essentially. And based on questions that I've had through emails, today I intend to do a kind of overlap. Excuse me. And we're going to look at section 2.1, domain and range of functions. And tomorrow I'll look at applications and so piecewise functions probably won't happen until Wednesday or Thursday. Now I look at my schedule over here, but we'll work our way through these. So the first thing we're going to look at is interval notation. So imagine I expressed some information that said that. What I'd be saying mathematically is that there's a variable x and it takes a value that's greater than or equal to 3. And we would like to write that information using interval notation. The convention is square bracket, comma, 3 to infinity. So if you want to imagine a number line, I know there's 1, there's 2, there's 3, there's 4. What you're really saying is that as long as x is 3 or anything bigger than 3, so you can indicate it with a kind of arrow like that, we're talking about values of x greater than 3. And so we could write it down kind of algebraically, x greater than or equal to 3, which is not that uncommon. Very rare, but couldn't we visualize it by drawing a little picture like I've just done here? And that would indicate that x would be greater than or equal to 3. And lastly, this fella here, which is one we're interested in, is called interval notation. So I'm going to give you a quick summary of all the different situations for intervals that can happen using interval notation. So the first one is this interval. And that's the same as all real numbers. So if the answer to your question is x can be any number you like, from -1 billion to +42, any number and any number in between those and any ones beyond those, all real numbers, that is the interval notation. If you had x greater than or equal to 3, we would do a square bracket 3 to infinity. On the other hand, if you do x greater than 3, we have to do an adjustment to the notation. Now, I know you call these everything parentheses in America, but I like the word bracket. That is a square bracket, and that's a curved bracket, right? So greater than or equal to 3 has a square bracket on the 3, means you can use 3 to infinity, right? Now, if you have greater than, do you see the difference? Okay, so interval notation, if you're trying to tell people x has to be bigger than 3 but not allowed to equal 3, that's your answer. It looks a bit like a weird coordinate, but it's an interval of values, right? 3 or bigger. Now you could go less than 4, less than or equal to 4. Now that would have negative infinity because you're going to be all the way over here to the left, and 4 with a square bracket. And if you did a less than 4, you'd be negative infinity to a 4 and a curved. There we go. Now, are we comfortable with those 5 things? Did they seem reasonably obvious how this kind of information could be transferred into interval notation? And the reason why we need this is that we're going to be dealing with domains, ranges of various kinds of functions. And the answer is going to be Well, the domain is all values of x bigger than 3, which would be this one, or less than or equal to 4, in which case this would be the answer. And we'd be writing the answer using interval notation rather than the algebra. But there is some other, a little bit more awkward situations, but they do happen. I call this a sandwich, just a made up name, you won't find it. And the reason I call that a sandwich is, to me, the x is sandwiched between 3 and 7. Right? That's why I call it a sandwich. And what that is saying is that x has to be a number between 3 and 7. Now, we have to figure out how that would be written down using interval notation. Now, since you're allowed to equal 3, you do a square bracket 3, comma, and you finish at 7, but you do a curved bracket at 7. Does that make sense? That if we're being consistent with our notation, wouldn't all the values between 3 and 7 look like that? Now, there's a couple of combinations of these. Couldn't you have both of them equal, this less than, this greater than? But I won't write all of them down, because if you know how to do one, can't you pretty much do the others? There is one I will put in. Now, if I asked you to write down what this interval, right, all values of x between -1 and 2, but you cannot use -1 and you cannot use 2 in interval notation, wouldn't it look like that? Agreed? Now, if you didn't know the context, wouldn't that also look like a coordinate to you? And we just have to live with that. That in mathematics, sometimes we use the same symbols, in this case, curved brackets, for different things. In the context of this question, I recognize that this means an interval. But in some totally different question, I might be saying, what's the coordinates of that corner up there? And you might say, oh, that corner up there has coordinates -1, 2. You might write that down, but wouldn't it be a different meaning when you write it down? When you know that the thing's a coordinate, then when you know it's an interval. Now, the last, and that's us finished after this, the last situation, obviously it's going to be the most complicated, and I'm going to draw a picture for it. What it would look like if I wrote a picture. So let's have -2, -1, 0, 1, 2, 3, keep going that way, keep going that way. So suppose I had, it starts at -1 and it's all the numbers going this way, and it starts at 2 and it's all the numbers going that way. So there actually, when you look at this, isn't there two distinct intervals, two distinct groups of values of x that would work in whatever that story happens to be? As long as x is less than or equal to -1, or if it's bigger than or equal to 2. Now, in interval notation, this guy here is written down as -∞, -1. And this guy over here is called, oops, make sure I put the brackets in right. Square brackets, because we're using them, right? Square brackets to infinity. But we have to indicate in some way that these two intervals are joined together to make a single answer. And we get round that by putting a symbol that looks like a big U. It's actually for the word union. So the answer is this interval unioned, joined to that interval. Are we good? You've seen that little union symbol before? Right. I believe in WebAssign, they'll let you put a comma there, which isn't good math, but you know, WebAssign does what WebAssign does. Okay, so these are what it looks like in algebra and what it looks like as an interval notation. So we're now going to look at domains and ranges of functions and expressing those answers using interval notation. So the first function that we're going to look at are domain and range of polynomial functions. Okay, let's show you what a polynomial looks like. A polynomial function is any function that contains positive whole number pairs of x. So any function, it only contains positive whole number pairs of x, right? It's not a fraction. It's not got square roots in it. It's not got negative pairs in it. So examples of polynomial functions. 3x cubed take away 2x. 2x minus 1. 2x squared take away 8x plus 1. They're pretty easy to recognize. Aren't polynomials just so many x squared plus or minus so many x's plus or minus a number, right? They all have that shape to it. Now, if any function looks like this, here is the domain. Unless there's other information to change it, the domain is going to be all real numbers, because domain of a function, at least, means all usable values of x. Now, if you look at any of these functions, you could put in any value of x you like, right? It's usable, and you'd be able to get an answer if at least you used a calculator, right? You plug it in here, it would work. Plug it in here, it would work. Plug x is 42, it would work. The domain is all real numbers. The range, well, it's the set of all possible answers to a function. To give you an example, if my function looked like this one here, the y values, and we're only really interested in the y values when you talk about the range, right? The answers are the y values. It can be as low as it likes, because this curve goes downwards forever. It goes as high as it likes. In this case, the range would be from minus infinity to infinity. On the other hand, sometimes polynomials look like this guy. And let's say that that guy there had a height of 2. Then in this case, the range of all possible answers would be, you could only get an answer of 2 or bigger. Does that make sense? Now, it's quite hard to tell, looking at a function, what its range is. It's very easy to tell what its domain is, right? They're all the same. But what the range is depends. Sometimes it's this situation. Sometimes it's more like that. So the quickest way is on your calculator, or as I'm going to do right now on Desmos. Here we go. Excuse me. Are you looking at a graphing program right now called Desmos? Okay.
Yes.
So I'm going to put in the first guy. So our first function was 3x cubed take away 2x. So 3x, oops, forgot my y's. Y equals 3x cubed. And what else do we want? Take away 2x. Oops. There. And the great thing about Desmos is you can adjust windows by moving your mouse around, and you can grab, if I can make it happen, because it's been awkward, but you can shrink it and stretch it and all sorts of cool stuff. Right. So would you agree this function goes down the way forever and up the way forever? So that would be minus infinity to infinity. Right. Now the next one is a straight line, and it's what, 2x take away 1. Would you agree the y values go downwards forever and upwards forever? So that's also minus infinity to infinity. But the third one I had was a quadratic, and that was 2x squared. Take away 8x, add 1. And if I shrink it a little bit and move things up, would you agree that this function goes all the way up to plus infinity, right? It zooms up the way. But there is a y value right there if I can click on it. Now, if you click on it, do you see how Desmos can tell you coordinates of things? Now, be careful about that. Isn't that telling me that the lowest y value is -7? So that would be -7 up to infinity would be your range. So I'm going to return back now to our whiteboard. And I guess I'll do it in green. I'll put the range here. This one was everybody. This one was everybody. But this one was -7 to infinity. Cool. And that's pretty much all you need to know to get the domain and range of a polynomial. The domain is always going to be -infinity to infinity, unless they tell you something else. And the range, well, if you put it into Desmos, you should be able to tell, right? Just look at it and see what kind of picture you get. Now, the next one is going to be the domain and range of what are called radical functions. And a radical function has a root. So examples of radical functions. Square root 2x take away 1. Cube root of x squared plus 2x. Well, so I'll do another square root. A square root of x squared take away 4. Now, we are talking about simple radical functions, right? A single square root or a cube root or a fourth root or whatever, right? Anything with a square root. Now, inside the radical, you'll probably see a polynomial. You see how there's a little x squared minus 4 here and a 2x minus 1. That's not as important. The thing that makes it a radical is the square root cube root piece, right? And the world splits into two distinct groups here. The first one are when the radical is odd. That means cube roots, fifth roots, probably you'll never see one, seventh roots and forever, right? And when you have those situations, as long as the thing inside is a polynomial, the domain will be all real numbers. Because I can plug any number I like in here and get x squared plus 2x. And I can find the cube root of any number. I can find out the cube root of 8, and I can find out the cube root of -8. Cube root of 8, for instance, is 2. The cube root of -8 is -2. All of those guys work, right? We don't have any situations where that's going to cause any kind of problems with the choice of x's. Any questions? We're good with that? Now, when the radicals is even, and what I mean by that is typically square roots, but you might see a fourth root and once in a blue moon a sixth root. Now, when it's that situation, all bets are off. When it's a square root, the term, try that again, the term inside must be positive. So what do I mean by that? Right. Let's take that one, for example. The square root of 2x minus 1. Its domain. You can only use values of x that make the inside positive. You're not allowed to have negative numbers inside square roots. If I said to you, what's the square root of -4? You might tell me some complex number it's equal to. But in this class, complex numbers don't exist. All answers are real numbers. So pretend you don't know what a complex number is. Square roots of negative numbers are not allowed. So this must be positive, which means that you're going to have to solve, hopefully, a relatively simple equation. So I use a rule called as long as you do it to both sides, it's okay rule. So I'm going to add 1 to both sides, and then I'm going to divide both sides by 2. So this is only going to be true when x is greater than or equal to -1. So x is greater than or equal to half, I should say. So the domain is going to be 1/2 or bigger. That makes sense? Now, how would I get the range? Well, I kind of do the same thing. When I just plug them into Desmos and see what we got. And can you trust me that in this case, your answer looks like that, because the function, when you get it, looks something like this, right? Goes all the way up and down. On the other hand, when you do this one, the range ends up being 0 to infinity, because when you do a little sketch of it, it looks like that. Right? It kind of starts at 0 and then it climbs upwards. So range is almost always going to be, just plug it into Desmos and see what you get. The domain, on the other hand, you really should, you're able to do algebra. Now, I've kept the best till last for this one. Yeah, I want the domain of this weird square root function. Oh, by the way, you can't call it x minus 2. The square roots don't work that way, right? You have to leave it alone. But what I can say for sure is that this has to be true. And I am trying to solve, when is this quadratic greater than or equal to 0? Now, I'm going to cut some corners here. You're just going to trust me on this. It's just for speed. If you plug x squared minus 4, right, into Desmos, can you just trust me that it ends up being this shape? Right? X squared minus 4. So if I plugged y equals x squared minus 4 into Desmos. Now, once I've got the picture in front of me, and I'll tell you a couple of key numbers. This is 2, and this is -2. Would you agree that this is only positive, meaning its y values are positive, when it's above the x-axis? Which means, aren't we talking about values of x this side and values of x going that way? So any value of x like -3 or -4 is going to give you a big answer. Any values 3 or 4 is going to give you a big, meaning positive answer. So in this question, the domain would be equal to anything less than -4, -2, union anything bigger than 2. Do you see, in this case, you got that either side thing going on. And you're just going to have to trust me on this, but if you do the range and you plug that into Desmos, and you get a different shape, but it ends up being pretty much that. Any questions so far about domain and range of radicals, square roots, cube root functions? Are we good? Any questions? This is your chance. Put them out the list. Check, check, check. Now we're going to look at rational functions. Rationals, basically an old-fashioned name for fractions. So you could have called them, today we'd probably call them fraction functions. And so we're going to look at the domain and range of rational functions, fraction functions. And examples. Right, so what do rational functions look like? They look like fractions. And in the fractions, the top, the numerator, and the bottom, the denominator, are polynomials, right? So there aren't any square roots or weird stuff, right? It's polynomial on the top, polynomial on the bottom. There's your guy. Let's get the range out of the way first. The range is the range of answers. And to do that, use your calculator or Desmos. Basically, just graph the thing and get your answer. There isn't any algebra you can do. And that's fine. Now, focus on the domain. The domain for a rational function is all values of x except for those values of x that make the bottom, which we call the denominator, 0. So the domain of a rational function will simply be all values of x except for those values of x that make the denominator 0. So that means we don't care what the top thing in a fraction is. It doesn't affect the domain. So I don't care that that's 10 or 10x. I don't care that that's 2x plus 1 or anything else. I don't care that that says 3x squared plus 1. All I care about is what values of x will make the bottom 0. Because those guys we can't use. So let's start with the first one. It's pretty obvious, would you agree, that x equals 3 is going to cause a problem. And if you try to do a calculation with x equals 3, won't you get 10 divided by 0, which is why it's a problem, right? It doesn't work. It's called undefined, if you want to know. So our domain, you kind of say it in a negative way. Our domain is everybody except for x equals 3. Now, in the algebra world, you would write it like that. Right? That's how you would write it as algebra. And if the question had said, tell me the domain in algebra, I guess you could have written that. But we're being asked to do it using interval notation, right? All of them are interval notation. So you might say, how on earth am I going to do everybody except 3? And the answer is remarkably simple, even although it might look a bit strange the first time. You go negative infinity up to 3, don't use 3. Union, start at 3, but don't use it, and finish at infinity. If you think that through, isn't that just a long way of saying you can't use 3? You see how it works? Interval notation. There's a hole in 3. That's a short way of saying it, right? There's a hole in 3. Can't get it. Now, the next guy is 2x add 1 over x squared minus 9. Well, I'm only interested in that problem, right? Is there any values of x where the bottom is 0? Right, could anybody tell me how you could approach solving this equation in the usual algebraic ways that you've learned in the past? There's 2 different routes, both work.
Is that the difference of perfect squares? Oh, sorry.
Okay. Like that? Is that what you're thinking? That works.
Yes.
Agreed. Now, factoring it, right? What does that lead to? Well, it leads to 2 distinct situations. If x is -3, you get 0. And if x equals 3, you get 0. So in our world, you cannot use 3 and you cannot use -3. And so we will write the domain down. And now it gets really ugly. Really, truly, interval notation is not very elegant in these circumstances. I don't want to use -3, so I go -infinity to -3, curve bracket, union, -3. But I then can only get as far as 3, and then I go 3 to infinity. Now, if you look at that notation, as ugly as it is, isn't it really basically saying -3 and 3 are the 2 guys that aren't going to get used, right? You start up to -3 and -3 onwards. You finish at 3 and then you start at 3 and you go on 3 onwards. And have you noticed that everybody is curved, right? Which means you can't use any of the endpoints. How's that look? Ugly, but doable? I hope, I can't guarantee it because I don't look at every single question or memorize them. But if you got a situation where there was 4 factors here, wouldn't this thing be even bigger and even uglier? But it would still be, you can't use 1, can't use 2, can't use 4, whatever it might be. Side issue. Why is there a curve at -infinity instead of a square bracket?
Because you can never actually reach infinity in either direction.
Yeah. So it's not really like a number like 4. Isn't infinity more like an idea? A thing that just keeps going? So curve bracket seems much more sensible. Yeah. In case you were wondering, that's a good reason. Actually, I think you said it better than the way I was going to say it. So that's good. Next one. Now, based on what we did every other question, don't we just look at when is the bottom 0? And that's going to tell us the bad guys. So one of the skills that you need are factoring, which is why there's some factoring in your project 1. Okay, tell me the 2 guys that work for this quadratic, the 2 factors.
X minus 8 and x plus 1.
Everybody agree? Which means this guy is x equals 8, so that means you can't use 8. And this guy has solution -1, and this means you do not use -1. And I am now deliberately going to do a mistake. So don't write this down. It's going to be wrong. Sometimes I make, in fact, a lot of the time I just make mistakes, but this is a deliberate one. Can you see that that is wrong? We always do things in order. So even if my factors came out in the order that they did, this is the order I should be doing them in. So it would be negative infinity, don't use -1, go all the way up to 8, but don't use 8. So this here is the correct answer. Do you see that it looks different from the one above? Even although they have the same kind of numbers and the same kind of curve brackets and all the other stuff, isn't everything kind of back to front and upside down, right? Correct, wrong. So always do your intervals from smallest to biggest, right? It's a good convention. Weber sign is pernickety. So if you don't do that, it will just tell you you're wrong. That will be frustrating. So let's have a few moments and look at what the homework looks like, just so you get an idea of how they ask it and so on and so forth. Right. Are you looking at, excuse me. Are you looking at question 4 right now? Is that what you see on the screen? Okay, good. Now, do you recognize a rational function? Very simple one. Would you look at it and say, hey, can't use 7? Agreed? Can't use 7. So go over here. If you can't use 7, you would type it in something like this. Curve bracket, negative infinity. Oops. If you write infinity, the word infinity, Weber sign will turn it into the symbol infinity for you if you find it hard to find where that is. Comma, up to 7, close the brackets. Now, I want to find the union symbol. So go to sets, and there it is there. Do you see it bottom left-hand corner? Sets, union, and then start at 7 and finish at infinity. And in this question, they only wanted the domain, which is pretty common, right? And if I hit submit answer, I will get a nice green check mark, right? Fingers crossed, go for it. Wrong direction, up here. Where are you? There, I've lost you. There, is correct. Any problems? Seem reasonable. Now, have you noticed that for fraction functions, they only typically ask you for the domain? But if you wanted to know what the range was, wouldn't you just plug it into the calculator and look at the picture, right? And it's plus to minus infinity or whatever it might be. That one's not unlike the one we've done. There's a radical. There's a oh, I didn't do question 7. So let me do a version of question 7. Square root g of t. And it's t squared plus 4. Sometimes the easiest answers are the ones that catch you out. Oh, it's a square root. Well, for a square root, that has to be true. Agreed? Now, if you sketch that, can you trust me? It looks like that. Which means everybody works. Right? Any value of t. So your domain would be everybody. So it's actually quite an easy question. And I'll zoom back over. Talk a little bit more about some of the others. There's a square root. We did something like that. If you were going to do question 9, wouldn't you go and do a sketch of x squared minus 1 and look at that picture and then find out what part of the shape is above the x-axis? Because that would make the guy positive. Right. Now, for this question 10, and I believe all the ones that follow, we enter the last stage. So let me go back to our notes now. And the last situation, the last stage, I've called them complex functions. These are basically functions that aren't one or other, but really a combination of the two. You know, fractions with square roots in them, right? Things like that would qualify under that. So now, for instance, suppose I had a function and it was the square root of 4 plus 2x all over x minus 3. And I want to find only the domain, right? So we're not interested in the range. We'd plug that into the calculator if we wanted it. There are, excuse me. I get some air here. There are two things that are happening. The bottom thing says, look, x can't be 3. You can't have a 0 on the bottom, right? Rational function. But there's also a top piece. And the top piece says, look, this guy has to be positive, which means this guy has to be greater than -4, which means this guy has to be greater than or equal to -2. So our answer has to be those two things being true at the same time. So how am I going to incorporate? You have to be bigger than -2, but you're not allowed to be 3. Well, this is how I would do it. I know I'm going to start at -2, but I'm not going to go all the way to infinity. I'm going to get to 3, and then I'm going to stop at 3, not use me, start back up at 3 and finish infinity. Do you see that that combination takes care of both those situations? Yes, it's bigger than or equal to -2. And yes, none of these numbers are 3. Now, the next one has a square root of x on the top, and on the bottom, it has a 5x squared plus 4x. I'm putting my numbers in here, minus 9. That'll work, right? And we've got this 2 thing going on. This one says, look, x must be greater than or equal to 0. It wasn't too hard to do that. And this one is, well, we need to find out if this is ever equal to 0, right? And there. Can you trust me that that's how it factors? Which means x equals 1, and you're not allowed that, so x is not equal to 1. And this one is x equal to 9/5, and that means x is not allowed to equal -9/5. So now we've got 3 different pieces of information. It has to be greater than or equal to 0. It's not allowed to be -9/5, and it's not allowed to be 1. And we have to put that together as a single interval like this one up here. Now, we got kind of lucky here. If x is greater than or equal to 0, won't that one get killed? Because this one will make that impossible. So that means I only need to start at 0. And won't that make that an irrelevant piece of information, right? I'm starting at 0, it don't matter. Oh, but I'm not allowed to equal 1. Yeah, does that make sense? That only those two really matter, because this one gets destroyed by that. How about this fella? times the simplest ones are the ones that will catch you out. Right, it's got a square root, it's got a fraction, right? That's the combination, right? Square roots and fractions. Would you agree that the top doesn't have a problem? It doesn't really change anything. Now, I do have a bottom issue. It's inside the square root. Well, if you're going to be inside the square root, that has to be true. Agreed? But you're on the bottom of a fraction. Why am I making that the real restriction instead of this? Why am I not allowing x minus 4 to be equal to 0?
You can't have 0 on the bottom.
Right, it's the fraction that caused it, not the square root, right? 0 was an issue, which means that this has to be greater than 4, and there's our domain. Curved bracket, because you're not allowed to use 4. Right, so the simplest looking ones could cause you trouble. Can you imagine you might do that question and put a square bracket 4 to infinity and getting really annoyed at WebAssign because it keeps telling you you're wrong. And you're looking, it says, there's nothing there, it has to be 4. What? Well, there, that's what's wrong, right? Curved bracket. Nothing there, you see. Right. This is really just tidying up questions. This is a version of question 15. And we're being asked to find the domain and the range. Now, when you are told what a function is, but you're given restrictions on what values of x you're allowed to use it for, this restriction is considered to be the domain. Right, so if they said from 1 to 2, my domain would be x is 1 to 2. So it's not a very nice situation, but that's what you got. Okay. Now, I need to know what that guy looks like, right, from 0 to 9. Because if I sketch it, which is what we typically do, isn't it, to find the range, we should be able to get it. So I'm going to do this my own kind of weird way. Can you trust me that if you plug the function x, 8x squared plus 4, it looks like a big happy face, right? Now, since you're only interested at x equals 0, doesn't that mean you start there? And you're finishing at 9, and let's pretend that's 9 there. Can you see that your curve looks like this? It has a starting dot at x equals 0, and it has a finishing dot at x equals 9. So won't the range be from here to here? The range of y's, right? The range of answers. From 4 to whatever that number is. How will I get the y coordinate of that point there? How could I find the y coordinate of that point there? Where its x coordinate is like?
The highest number of the restriction?
Yeah, so what would that be? So f of 9 would be 8 times 9 squared, add 4, 8 times 81, add 4, 648, add 4, I hope I did this right, 652. So we would finish at 652. So the highest number on the restriction was x is 9. The highest value of the function would be whatever that is equal to at 9. Are we good with that? Right, now, since I've got a few seconds left, I'm going to see if Desmos can do that same thing for me. I'm typing in as we speak then. Oh, let's zoom over so you can see it. So I'll put it in. So it's going to be y equals 8x squared plus 4. And boom, there we go. It's this guy here. Now, if I hit the little graph setting thing, I can restrict the x's from 0 to 9. And then, oh, that scale's ridiculous. Okay, I'll try it again. Right, I'm just playing about with the scale a little bit. I think I'm about ready. Yeah. There's 0, right? And 9 is 1, 2 is on this box here. Boom. Come on, come out. Well, it's darn close to it. There we go. 9,652. Can you see the extreme value? And I believe that's all we have time for, but hopefully I've covered as much of the domain and range that might or might not be causing you some issues. For attendance, and then just leave as soon as you've done this, put your last name in. So go to chat box and put in your surname, your last name. And I will see you again tomorrow. It'll be Zoom. I'm feeling a lot better. I'm hoping to be back in person by Wednesday, right? So, but tomorrow's going to be another Zoom. Put your last name down as in attendance, and then bye-bye. And I'll hang about for any questions you might have.
I had a
before.
question about project 1 and
Yes.
how we were submitting that, since it was supposed to be submitted in person today.
It's going to be submitted in person when I see you on probably Wednesday. So
Okay.
you've got a couple more days to do it because of that.
Okay, awesome. Thank you.
I have a question about the last question on that project 1.
Sure. Let me go find it while you're doing that. Okay, got project 1. I'm just loading it up as we speak. I'll jump over at the screen. That way you can just double check it's what you thought it was. You know, that I'm doing the same questions you were expecting. Right, put it on a full screen. Here we go. This one here, the John travelled home with his mother one.
Yes.
Oh, you don't like puzzle questions, or you just don't like this puzzle question?
I just don't like this one.
Okay. So John travelled from his home to his mother's home, which is 200 miles away. So you'll see this in a minute, but I'm writing down kind of on a piece of paper. There's John, and there's his mum's house. And I'm writing 200 miles in between. I gotcha, right? He then returns back home the same day. During these journeys, he's noticed that his speed was 10 miles per hour faster coming home, right? So I'm going to do his speed from John's to his mum, and I'm going to call that X. And then I'm writing down the speed from his mum's house back to where John lives, and he's 10 miles an hour. I'm going to call that X add 10. And the last thing I'm going to write down is that the total time of the journey lasted 9 hours. So I've pretty much got everything that story did. I've just kind of maybe written it down a little bit more visually and a little bit more algebraically. So John to his mum, 200 miles.
Okay.
When he goes that way, I don't know what the speed is, but I'll call it X. When he comes home, it was 10 mile an hour faster. So I'm going to call it 10 add X, right? Now I'm going to find the 2 times. The time from John's house to his mum. Well, that's the distance travelled divided by X. Right, distance over speed. Now I'm going to find the time to go from his mum's house back to where John lives. And that's also 200 miles, but his speed was X add 10. Okay. Now I know the total. The total took 9 hours. And I know that that's made up of this guy plus this guy. So there's my equation. Are you with me so far?
Yeah, I wrote down everything up to, like, I already had.
Up to about here? Or here?
Yeah, up to about there, yeah.
Right. So what we're going to have to do now is some heavy duty algebra. We're going to have to take these two fractions, right? And we're going to have to try and figure some way to get rid of the fractions, because trying to solve equations with fractions in them is really a non-starter. So I'm going to do a clever technique that I call, I've used it today, as long as you do it to both sides, it's okay, Rob. So I'm going to multiply both sides by x. If you multiply this guy by x, you get 200. If you multiply this by x, you get 200x over x add 10. And if you multiply this guy by x, you get 9x. Are you comfortable about times x times x times x? This is what you've got.
Yes.
Now I'm going to multiply both sides again, but with x add 10. So I'm going to get 200 x add 10s plus 200x equals 9x x add 10. Multiply that guy by x add 10, multiply this guy by x add 10, multiply this guy by x add 10. Looking good?
Yeah.
Now, have you noticed that we now have a quadratic, if we will, in a few lines? No more fractions. So here goes. Distribute 200x plus 2000 plus another 200x equals 9x squared plus 90. Are you comfortable with that line?
Would it be 90x?
Yes, it would be. Thanks for catching me. You comfortable with it now?
Yes.
Right. Well, let's tidy up slowly. 400x plus 2000 equals 9x squared plus 90x. Let's subtract 400x from both sides. And let's subtract 2000 from both sides. We are now looking at this really ugly, just checking anything weird that I may have done wrong. This ugly and quadratic. Great.
Mm-hmm.
Now, if it was a nice quadratic, wouldn't it? Wouldn't I just factor it? But since it's not a nice one, what I can do instead is just get the answer using Desmos. So here goes. Into Desmos, I will put 9x squared take away 310x, take away 2000. Now, if you look carefully at this quadratic, do you see that there are two solutions? There's some weird one over here at negative 5.5. I'm not even going to bother with that one, because wouldn't that mean he was driving backwards? Right, so the only one that makes sense, do you see, is that one there? And wouldn't that be a speed where x is 40?
Yes.
Now, I'll go back just to tidy things up and finish the question off then. We know that this time here, the speed he takes to his mum is called x, so that's 40. And won't the speed coming back, that will be 50. And doesn't that make perfect sense now?